This is Linked Data Engineering, lecture number 6, Advanced Linked Data-Based Applications. In part 4 of the lecture, we want to continue with named entity resolution and give you a more detailed look on this process. So let's remember, named entity resolution was, in the end, the mapping of a character string to an entity in a knowledge base, which can, of course, be related to problems of ambiguity, which often is the case in natural language. So Neil Armstrong here, for example, should be mapped to the entity Neil Armstrong of a knowledge base. We use, as an example knowledge base, DBpedia. How does this process work in general? First of all, you have to detect all the named entities in the text. And then you determine the possible candidates for these entities. And then you filter the entity candidates, and in the end there is a disambiguation process according to a given context. And in these 4 steps we want to look into detail now. First of all, we want to detect all the named entities in the text. Therefore, you have to do a linguistic analysis with so-called NLP techniques, natural language processing techniques. The first thing you do usually with natural language is you do a part of speech tagging, which means you try to identify what part of speech is a specific character string, a part of your sentence. What is it? Is it a verb? Is it a noun? Is it a preposition? Is it an adjective? Is it a conjunction or whatever? So there are lots of interesting programs which do this called POS tagging. I have here the link to one of these parts of speech taggers. Just click on the link, copy our text into the field and then simply press process, and then you will see something like that, which in the end underlines or highlights each of the sections of your sentence in a different color and tells you what is a pronoun, what is a verb, what is a number, what is a noun, what is a determiner, what is a conjunction, and so on and so forth. For our named entities, usually interesting are definitely nouns, or which can be adjectives, which can be part of nouns. So nouns here in our example are gray highlighted. So for example, Neil Armstrong is a noun, commander is a noun, Earth is a noun, tranquility base is a noun, and so on and so on. So this is the first step, determine the nouns because they might be interesting. For further filtering process, you can also apply a named entity recognition. Also, this is a technique which is around there for quite a while in natural language processing. I have again provided a link for you that you can try out. Simply copy our text to that link, say named entity recognition, and then, for example, depending on what kind of named entity tagger you choose, here we have one with 3 different categories. A specific category or class will be assigned to an entity. So here we can distinguish between persons, locations, and organizations, and Neil Armstrong has been tagged as person, Houston has been tagged as a location, and Tranquility Base as an organization. Please keep in mind that these are automated processes, so they are not always correct. So not 100% of the output of these programs is correct. But, even a human can make mistakes. So also these programs, of course, are prone to error. For example, if the context is insufficient or the use somehow is misleading, then probably also these programs will make errors. Another thing you have to do when you detect the named entities is to look which part of a text belong together, for example. And for this you do an n-gram analysis. You simply look at the single components of the text and try to make sense whether, let's say, each single word, this is a 1-gram analysis, would be mapped to a specific entity, and then you look at the 2 word strings, for example, like mission control or control room, or you look at 3 word strings. This is a 3-gram analysis, mission control room. So the decision which one then is the entity you should choose as a candidate is, of course, a difficult decision. You can take all of them, and then you will see for mission control room, possibly you have 3 1-grams which have already some more than 3 entities which it can be mapped to. Then for the 2 grams you have additional entities, and then for the 3 grams you will have a rather specific entity. You can also apply heuristics which say I always try to choose, if there is one, let's say the most specific description of an entity which consists of the most words. So 3 gram would be chosen over 2 gram over 1 gram. Could be a possible strategy. Might always or might sometimes lead to error. You don't know. So this of course is right now also a subject of ongoing research. But nevertheless it's interesting for you to find out how named entity resolution really works. In the end, what you also have to do in your sentences, of course, you have to do some kind of normalization, which, for example, means that you try to use a stem of a word, or you try to find a normalized spelling, for example, a normalized transcription for foreign language names and stuff like that. And this is a process of normalization that you also use to map then the label you have in the text to labels which are associated to entities in your knowledge base. Okay, step 2, let's assume we have found all the named entities. Now we want to determine the possible entity candidates. For this, we need something which is called a gazetteer. A gazetteer is something which maps semantic entities to all assigned labels. So we list all the assigned labels to one specific semantic entity. And for the last version of DBpedia, there were about 40 million labels for 9 million DBpedia entities. And as you see here, there are lots also of synonyms. So several names can be assigned to one entity. And in DBpedia, you will find this via the following connection. There will be a so-called redirect between 2 entities. You can experience this, for example, if you go to Wikipedia, then you will find via synonyms of a specific entity that you look up or article that you look up in Wikipedia, you will be redirected to a normative page in the end. And these are these redirects. So these redirects usually work in the way that, of course, this entity has assigned a label and this entity has assigned a label, but only the redirected entity, so this one, where it points to, will have also all the other properties that usually are associated to that entity. This one is only a synonym, and from there goes a redirect to the original entity. You have to know that. And of course, this situation can also be vice versa. There can be so-called homonyms, which means you have a string which can have possible meanings. You have one name which is mapped to several entities, and in DBpedia this is called disambiguation. For example, in Wikipedia, which underlies the DBpedia, you will sometimes find so-called disambiguation pages. If you have a word which is highly ambiguous, then usually you will be led to a page where you can choose between the different meanings. So this is the so-called disambiguation page. So this means the entity which is ambiguous is this one, and from this you have a disambiguation which goes to several entities. So this is something which also has to be considered when you collect all the possible labels which are out there in DBpedia. So if you try to create this kind of gazetteer from DBpedia information, what you have to do is you have to resolve chains and cycles which might be in the DBpedia link graph and which consists out of redirect and disambiguation links which might cause a cycle. So for example, you might find a structure like that one, and the point is here, let's say the source entities are those which are not in the end labeled with a redirect. So for example, this one does not have a redirect going out and does not have a disambiguate going out, and this one also. So this one and this one would be the leaves of that graph. So the strategy usually that you do here, simply you try to gather all the labels in a cycle or in a path that leads to that leaf of that graph. So for example, if we look at that one, of course we put label A2 into the blue one here. We put also label A1 into that, and we put also label A3 into that. Then we have a cycle, again A2 we have it already, so therefore we don't consider it anymore. So this is all the labels that will be put into here. And then we look at the next leaf node, it's that one, and then we see, okay, there we need A5, it will be in that node, then we will need A2, A1, and we will need A3, and all these have to be put onto that node. So this will be the names which refer to exactly this entity, and this will be the names which exactly refer to that entity. And in this way, you can build up a so-called gazetteer that you are using to determine all the possible candidates for a given text. And then, for example, if you are looking for all the possible candidates for Neil Armstrong, you may find a candidate resource list which looks like that. And these are all the resources which have the RDFS label or FOAF name Neil Armstrong. And you see here, of course, you have the resource Neil Armstrong, but you also have one Neil Armstrong, which is an ice hockey official somehow. Or you have the Neil Armstrong Air and Space Museum, or you have something which comes here from Wikidata, and we have no idea what it is. What can furthermore help, for example, is if you are using information from the knowledge base and, for example, from the entity recognition process. For Neil Armstrong here in the text, we have found out that this must be a person, so therefore we can filter here only these entities in the knowledge base which refer to a person. So we will end up, of course, with Neil Armstrong. Here it's a Wikidata resource, and we will have also these ice hockey official. And here the Air and Space Museum, it's a museum or it's a building or a location. This, of course, is not a person, so therefore we can pre-filter this and we shrink the number of potential entity candidates. So this is a filter process based on named entity recognition. Then if you come to the disambiguation process, things are complicated. To distinguish and to understand the data, you have to do this disambiguation according to a given context. And the analysis of context is still subject of ongoing research. So we have found out that you have to consider different context dimensions. There is a temporal context, so according to time. Time tells you something about, let's say, if I'm talking about the President of the United States, of course, another entity will referred to in 2016 than in 1916. So this is a temporal context that is important for disambiguation. Then also there is a spatial context important. If I talk about a president, it determines if I talk about a specific country, for example, if I talk about the United States, or if I talk about Germany, or if I talk about France. So that will be different persons. So this is a spatial context. And there can also be social context, which might have some relevance or which determine in the end the relevance in your decision for which entity has to be chosen in the entity disambiguation process. And there are several dimensions of context description. So those, for example, class diversity, which gives a level of ambiguity, or the level of structure, so how complicated is the underlying ontology, how reliable is the source where the context information comes from, how diverse is the source, and all these influences accuracy, ambiguity, and relevance. If you are further interested in exactly these notions of context analysis, please refer to that research papers from 2013 from our group. Context analysis, in the end, is then the basis of the subsequent analysis of disambiguation. And what we do here, for example, are two different techniques. First, I want to show you the link graph analysis, which comes from the Wikipedia link graph, how Wikipedia articles are linked to each other. If I take the link graph of these Wikipedia articles into consideration, and I look at them for all the candidates that are here inside my example, you will end up in a graph like that one, which in the end will tell you almost nothing. What you have to do to learn something about this graph is you have to level the graph. So here we see different levels. So the basic level here at the bottom, these are all the entities which are labeled with the word Earth. These are all the entities which are labeled with the word Eagle. Here is Houston, Mission Control, Neil Armstrong, and Tranquility Base. What you see then is the connections among these entities. What is interesting is the connection between entities among different layers. And of course, what is also interesting, if, for example, like in this layer, there is only one possible entity, there is no high ambiguity. So this is unique. So which means this one I can take as a context for the others, because this one is already fixed. I don't have the choice to make. I don't have to do a disambiguation. Then I go to the next one. So this one, Mission Control, also only one. So both of them can serve as the context for the resolution of the others. Then I go to the next one where I only have two different choices. And I see here, for example, that one of them is not connected to any other level. So it should be this one, which makes it quite easy. So we have the first three already determined. And then we have to find out which of the others might be the correct one for Houston, Eagle, and Earth. And this gives you somehow a notion already how this disambiguation process might work. Speaking of it in a more mathematical sense, I have plotted here these single layers here. I have turned it by 90 degrees, and this is exactly the same graph for Eagle, Earth, Neil Armstrong, Houston, Tranquility Base, and Mission Control, or it should be somehow like the same graph. What I do first is, of course, I remove all these nodes which are not connected or interconnected between the layers. I only want to identify the so-called connected components. Component here, one component is one layer. And these are nodes which connect these components. And then you see I have several. Now I try to look for the longest connected components. So these components which cover most term partitions. And I see here, this is the fat one, that I have here a partition which covers 1, 2, 3, 4 of 5, or it's even 5 of 6, yeah, 5 of 6 layers. So this means this kind of ambiguation or disambiguation is highly likely. And furthermore, I see that, for example, here are even strongly connected components. So there are further connections among exactly these ones. And these strongly connected components furthermore consolidate my disambiguation and show me that it's really highly likely that these 4 are definitely or most likely the ones which have to be chosen because they are connected to the others. They are related to the others. And usually if I say in a word, or if I mention several entities in one sentence, it is the basic assumption that these things usually are related with each other. If I put things together which are absolutely not related with each other, then the sentence is rather difficult to understand. In the context of the moon, if I talk about Neil Armstrong in context of the moon and the moon landing, then of course words that occur there in my natural language text are related with each other. And I simply use this fact with a reference knowledge base, with a reference text corpus to make exactly these basic assumptions visible in my corpus and then use it and use these statistical probabilities that you see here, be it a graph analysis or be it a connected component analysis. The only problem with the graph is that the one you saw here, the small one with the 6 layers, it's quite simple. Usually graphs look like this. You have hundreds, thousands of possible entity candidates because you do not only look at one sentence, you look at least one paragraph or even one page of the text. And then, of course, this is an immense problem which requires lots of computing power. The other case co-occurrence analysis, it works quite the same. There you look at texts which describe the entities, and for this reason we use here, for example, Wikipedia pages describing Neil Armstrong, either the astronaut or Neil Armstrong, the ice hockey player, and we simply look how often do the other entities, the other words occur in these 2 articles for Neil Armstrong, the astronaut, and Neil Armstrong, the ice hockey player. And we choose the one where most of the others occur. Simple statistical argument, it usually is labeled as co-occurrence analysis, which gives us a rough heuristic to say, yeah, this is most likely that exactly this is then the right meaning. So the general approach is with different techniques that you can use for disambiguation. Start with the most reliable algorithm on the most accurate and most reliable data, and then resolve the remaining ambiguity with less reliable algorithms on less reliable data. In our research, we have made a prototype, or we did research in exactly this area in named entity resolution, and we have a prototype which is called KEA, K-E-A, like the bird from Australia. And this does a connected component analysis on graphs, it does a co-occurrence on Wikipedia text corpus, it does a popularity-based link graph analysis, and it also does something which is called negative context analysis, which means we try to find out what it cannot be under no circumstances, and we simply exclude then things from the possible candidates with this negative context analysis. If you are further interested in research in that, simply look at the articles which are referenced here at the bottom of the page. Then you can read more about our research in named entity resolution. This closes the section about named entity resolution. In the next part of the lecture, we want to talk about another application. For example, when you have already annotated a document, so when semantic annotations are there, for example, after named entity resolution has taken place, then you can put on top of that an improved retrieval procedure, which is called semantic search. What semantic search is and what can be achieved with semantic search, you will learn in the next part of the lecture.